Let's start today with a discussion on free energy of formation. Free energy of formation is a tabulated set of data that can be employed due to the fact that the free energy is a state function. We can use it to find the enthalpy of any reaction without worrying about the free energy it takes to build the elements in their standard states, as long as we just claim that we assign elements in their standard state a zero free energy of formation. Then all the free energy it takes to build any compound or molecule goes into the compound or molecule itself. Now the benefit of this is if we start reacting things, which means we tear certain reactants apart and take the pieces and parts from the reactants and put them together to make new products in a chemical transformation. Well, since the reactants and products have conserved numbers of atoms, we're not going to sweep any atoms under the rug or pull any atoms out of thin air, then we don't really need to worry about the free energy of formation of the individual atoms that went into building the molecules that are balanced on both sides of the chemical equation. All those individual terms for the atoms would cancel. All we need to know are the free energy of formations of the compounds and the molecules, and then because the free energy is a state function, all it matters is that we get to the final and from the initial states. So delta G of the reaction is found by taking the delta GF of formation of the products minus the delta G of formation of the reactants. Now there's a little superscript 0 attached to these delta G of formation values. That is because the delta G of formations are tabulated at standard ambient conditions. Standard ambient conditions means that the delta G of formation is tabulated for materials at 298 K or 25 degrees C and 1 bar measured as the external pressure. Now again, for elements in their standard states, and of course you have to know what the standard state of each element is, like O is O2 gaseous, mercury is Hg liquid, and so forth. But we assign a value of 0 for all elements in their standard states. Now again, the trick is that when we use these in a form of reaction, since the elements on both sides of the equations are balanced, they would have canceled anyways, and we wouldn't have to add in or subtract out any values for the formation of the individual atoms themselves. Okay, so again, probably on the final exam, you'll have a chance to use the idea of calculating a delta G of a reaction from the formation values. Let's look at how we can study the variation of the Gibbs function with temperature. We can do so by beginning with the combination first and second law fundamental equation for the increment of change in the Gibbs function. That would be dg is v dp minus s dt. Then what I can do is I can, because dg is a state function and an exact differential, and because it is a function of p and t, I can say that the increment of change in the Gibbs function is the slope of the function in the GP plane times the increment of change dp plus the slope of the function in the GT plane times the increment of change dt. So because again it's a state function and an exact differential, I can independently take these independent variables, look at how the Gibbs function changes with regard to these independently, and get the total change of the Gibbs function. By comparing the first two equations, I note that an expression for how the Gibbs function varies with temperature at a constant pressure, like in a laboratory, is equal to minus the entropy of the system. So if I use the definition of the Gibbs function as being h minus Ts, and then solve that for S, I can say that the variation of the Gibbs function with temperature is g minus h over t. Now what I'm going to do is subtract g over t from both sides, and I get that the variation of the Gibbs function with temperature minus g over t is equal to minus h over t. Now then what I'm going to notice is a trick with the differential of g of t. And if I multiply both sides by 1 over t, I get that 1 over t times the variation of the Gibbs function with temperature minus g over t squared equals minus h over t. Now you may ask yourself why I do this. We will see why I do this on the next slide. But before we go to the next slide, let's take a look at the graph to the left, which is showing the plot of the Gibbs function versus temperature for a given material. And what you'll notice is that there's a line representing the behavior of the Gibbs function while it's in the gas phase. There's a line representing the variation of the Gibbs function with temperature while it's in the liquid phase. And there's a line representing the variation of the Gibbs function with temperature while it's in the solid phase. Now what you might notice, if you look closely at these slopes, is that they're all negative. And if we turn to the middle expression in the equation set, I see dg dt at fixed p is equal to negative s. Well, s is the entropy. Entropy is positive, and there's a negative sign in front of that positive entropy. So what we're learning then is that the variation of Gibbs with temperature is always a negative slope. So you will note that all three of the slopes of these phase plots are negative. Next, what you should note is that the solid line has the least dramatic negative slope. The gas line has the most dramatic negative slope. This goes right along with the fact that the Gibbs function is, the entropy value of a gas is greater than the entropy value of a liquid, which is greater than the entropy value of the solid. So I would expect that the solid curve would have the least slope, the liquid curve would have an intermediate negative slope, and that the gas curve for the G versus T plot would have the most dramatic slope. Let's continue the derivation from the previous slide, where we are manipulating the function, the variation of the Gibbs function with temperature at constant pressure. From the end of the previous slide, we saw 1 over t dg dt is equal to, minus g over t squared equals negative h over t squared. So now what I'm going to do is another trick. And notice that I can combine the two terms on the left-hand side and use the product rule on the function g over t, take the derivative of that with respect to t, and it is equal to the two terms on the left-hand side. So I can write then that the partial of g over t with respect to t is equal to minus the enthalpy over t squared. Now what I'm going to do is make a change of variable from dt to d1 over t. And I do that by saying d1 over t dt is equal to negative 1 over t squared, so that the partial of t is equal to minus t squared times the partial of 1 over t. I just algebraically manipulate the expression above. So I'm going to substitute for the partial of t, I'm going to substitute minus t squared times the partial of 1 over t. And when I do that to both sides of the equation, I find that the partial of G over T with respect to 1 over T is equal to the enthalpy of the reaction. So the way that the Gibbs function varies with temperature, and this is known as the Gibbs-Helmholtz equation, is that a plot of G over T versus 1 over T will be a straight line, and the slope of that straight line will be equal to the enthalpy of the reaction. So by manipulating the exact differentials and partial expressions, we've come to this theoretically derived conclusion for the behavior of the Gibbs function with temperature. And of course, immediately when Gibbs and Helmholtz proposed this, experimentalists such as Joule and others went out looking around to see if they could find this kind of behavior, and it was verified. So again, what I want to emphasize to you is we seem to be doing a lot of crazy mathematical manipulation of thermodynamic quantities, but it led to an incredible extension of our thought of the way science works. This was a completely abstract thought experiment, mathematically verifiable as to how the Gibbs function should vary with temperature. And then after the mathematical manipulations are completed, experimentalists could use the results of the theoreticians and go look for these kinds of phenomena. And when they went to look, lo and behold, they were verified. This, again, I cannot overemphasize to you the quantum leap that science is taking when we go from just a phenomenological observation of the world around us to this abstract prediction of behavior and then designing experiments to go look for this abstract behavior. This became the norm by the time we came to the 20th century. It was the norm in relativistic effects, gravitational effects, quantum mechanical effects, that we began to use mathematics to lead science, and then the experimental techniques followed the predictions. We can play some similar games to investigate how the Gibbs function varies with pressure. Again, we begin with the combination first and second law, fundamental equation of thermodynamics for the variation of the Gibbs function, and that is VdP minus SdT. Then, relying on the fact that the Gibbs function is exact, I can look at it from the point of view of the increment of change in the two independent variables P and T, as we see at the second equation. Then, by relating the second equation to the first, I see that the change in Gibbs function with pressure isothermally will be equal to the volume of the system. Now, as we did before, let's look at the plot on the left of G versus P and look at how G versus P varies for the three phases of matter. Note, first of all, these are all positive slope values. That is because, of course, volume is a positive quantity. And also notice that the slope of the liquid and solid plots are very similar, but the slope of the gas plot is very dramatic. This is because the molar volume of solids and liquids are pretty much the same when you're in the liquid phase and the solid phase. A little bit difference, not much, so the slopes are rather equivalent in those cases. But however, in the gas phase, the slope is much more dramatic. For instance, liquid water occupies a volume, if I take 1 mole of liquid water, it would occupy a volume of 18 milliliters. Now, how do I know that? Well, 1 mole of water is 18 grams. Water has a density of 1 gram per milliliter, so that 1 mole of water occupying 18 grams would be 18 milliliters. But according to the ideal gas idea, 1 mole of water vapor at STP would occupy 22.4 liters. That is dramatically different. That's about 11 and a half, or a little more than 11 2-liter Coke bottles of volume as compared to a partial filling of a 50 milliliter graduated cylinder. Now let's return to the idea of how the Gibbs function varies with pressure. Let's note that if I do an isothermal experiment, dG is VdP, and therefore when I integrate that expression, I integrate both sides and I allow the pressure to vary from some initial to some final, and simultaneously the Gibbs will vary from some initial to some final. Both of these values being state functions, I can do them independent like I'm doing here, and I can just evaluate these integrals at the limits of those points of change. If I assume the gas being ideal, I can substitute for volume nRT over P. And then when I integrate both sides of that equation, I will get that the Gibbs function varies with pressure isothermally as nRT ln PF over PI. Now let's take a big, bold move with regard to what we're going to do with our thermodynamic quantities. So far we've done and examined, all this time during this semester, we've been examining physical change. And what I mean by physical change is we've pushed on our gas, squeezed on it, heated it, cooled it, did all these sorts of things to it, but we did not allow the gas that we were operating on, we did not allow it to change composition. We did not allow it to change from one form into another. And of course, what would the study of chemistry be and the chemical thermodynamics be if we did not allow for change of composition of our substances? So in order to introduce chemical change, we need to slightly modify the expressions we have used so far, and then we can look at how the energetics of the internal energy, the energetics of the enthalpy, and the Helmholtz energy, or the free energy, any of these forms of energy, and that's what we're going to do. We're going to look at the forms of energy and how they vary when we allow the expression to change composition. And when we do this, we will introduce a new quantity. And the name given to that new quantity is the so-called chemical potential. Now, this is a very cleverly named quantity, the chemical potential. It is much akin to other values that were introduced in physics to indicate the possibility of energy being evolving in a system. For instance, I can name two right off the top of my head, and those would be the gravitational potential that the Earth supplies. So if you are a certain distance from the surface of the Earth, you experience, not only you, but all objects experience a certain gravitational potential from that distance. And if you drop objects from that distance, in theory, they all fall at the same speed because they're experiencing the same gravitational potential. Now, when they hit the Earth, they will hit the Earth with different energies because the potential energy at a height h is equal to mgh. The gravitational potential at a height h is just gh. So in actuality, the gravitational potential we can say is intensive. And to get the extensive energy from the gravitational potential, you multiply the gh value by m. Now the same thing is true in the electrical realm. We have electric potential. An electric potential is what we more commonly refer to as the voltage, but it's a measure of the energy of the field per unit of charge in the field. And it's equal to K, Q over R, where Q is the charge causing this potential. Now, if we multiply that by a second charge Q, you will get the total energy that a charge will experience at a point in space. Now, the voltage that any charge experiences in space, no matter what charge is the same. But then if you multiply by the amount of charge, you'll get the energy that it experiences. So again, a voltage or electric potential is in many ways an intensive property as well. It's extensive when you scale it by the amount of charge placed at that point in space. So now we're going to introduce this chemical potential, which will be the energy per mole of material, and in that way it's an intensive value of energy stored during a chemical process. Then as the number of moles change, we can multiply this chemical potential by the number of moles experiencing that change, so we can multiply this intensive by the moles to make it an extensive energy of the chemical process. So this new quantity chemical potential we will introduce by just simply modifying our expressions ever so slightly, and it will allow us to examine chemical change in a reaction. Let's first look at how we can modify the internal energy to account for chemical change. The expression you see at the top, du is TdS minus PdV, is completely general for any material, but in particular, it's completely general for the change in internal energy of that material, as long as it is not undergoing a change in composition. So for a physical change on a material, this expression holds. Now, of course, if it is, because it is an exact differential, I could write that, and since u is a function, as we see here, of S and V, then du is equal to du ds at fixed V plus du dV at fixed S times the increments of change ds and dV. Okay, so I am only going to slightly modify the expression to account for change. I'm going to put on a third term that is now a function of the number of moles of the material that is present. So if I have a mixture of components, A and B, I would have a UA and a UB, and I would have to have an NA and an NB for the various components that I'm changing here. Okay, so all I'm going to do is take the original fundamental equation and add a new term, which right now looks like a fudge factor, that I'm going to call mu times dn. And if now I'm expressing u as a function of three variables, s, v, and n, I have to now slightly modify my expression for the exact differential. That would be, now I have my slope du ds, but now that's in as long as I have the v and n planes fixed. I have my slope du dv, but now that is in terms of the s and n planes being fixed. And now I have introduced a new plane of change for the internal energy with the amount of material present, as long as S and V are held constant. So now by identification of the third equation with the fourth equation, I now know how the expression for the chemical potential can be given based on the change in internal energy with composition. As the internal energy changes with composition, as long as I do that adiabatically and isochorically, I would have the chemical potential or how much energy is available during reaction for a given process. Now again, if I were to extend this to multiple components undergoing change, I would just have a term mu1, mu2, mu3, and so forth, where I'm defining mu1 as being the partial of mu with respect to n1, still holding S and V fixed, but also holding the composition of all other species, N2, N3, and so forth, fixed as well. So the conclusion on this slide is that the chemical potential can be found from how the internal energy changes with composition at fixed entropy and at fixed volume, or meaning in an adiabatic isochoric process, the available energy from a chemical change is how the internal energy changes as the number of moles change. Now look at how we can similarly modify the enthalpy expression to account for chemical potential or change in composition. If energy is expressed as heated constant pressure at what enthalpy is, we can use this recipe to find how much energy is available in a chemical reaction to be used as a result of changing the number of moles of a disappearing reactant and forming moles of an appearing product. Okay, so again, we begin with the fundamental equation, but this time in terms of enthalpy. That'd be TdS plus VdP, and then expressed as an exact differential. It's the slope of change of the enthalpy in the entropy plane, fixed pressure, times the increment of change of entropy plus the slope of the enthalpy with pressure in the adiabatic plane times the increment of change of pressure. Now, to modify this expression, very simply, I'm going to take the top equation and add a term with a fudge factor mu expressing how the enthalpy varies as the number of moles of a substance change. So the third line down is the enthalpy, increment of enthalpy change in chemical reactions. The first line is the increment of enthalpy change in physical processes. Now, H is still an exact differential, but now it's a function of three variables, SP and N. So I can write it as three partials of change with respect to change in those increments of those planar increments, ds, dp, and dn. And by comparing the third and fourth equations, I can recognize that the chemical potential can be expressed from the enthalpy as how it varies with composition with entropy and pressure. Okay, now, is this value going to be different? No, it won't be different. Numerically, the chemical potential has got to be the same in that reaction. This mu number is not different in value than the mu number we found on the previous slide. However, it is determined in a slightly different way. The previous mu was determined from how the internal energy changed with composition at fixed entropy and volume. So in an isochoric adiabatic experiment, you monitor the change in internal energy with composition and you'll get a number. Here I'm saying in an adiabatic isobaric experiment, now you vary the enthalpy with composition, you'll get the same number. So this chemical potential is the same, it is just evaluated under different conditions. Now again, if we have several components changing composition simultaneously, you would just add a mu term for each of those changing composition components, and you would express the chemical potential due to change in composition of any one of them while you're holding all others fixed. Let's consider this, continue this theme, but this time we will look at how we can modify the Helmholtz function for change in composition. Again, you begin with the fundamental equation for an increment of change in the Helmholtz function. That'd be minus PdV minus SdT. And since it's an exact differential, it can be expressed as we see in the second line. Now again, of course, this is for physical change of some material, how its Helmholtz energy is changing. Now I want to introduce chemical change. So I will just simply modify the previous two factors by a fudge factor mu times change in composition. Then by looking at it from the perspective of an exact differential, I can identify exactly the mathematical form of mu. And I will note that mu, if A is a function of now Vt and N, that mu can be identified as how the Helmholtz energy changes with composition in an isothermal isochoric process. So if V and T are held fixed, the chemical potential can be found from how the Helmholtz energy is varying. Now again, let's be clear. This must be the same chemical potential that the process has, but now I can identify it from a different set of parameters on a different one of the thermodynamic energy representations. So mu is the partial of A with respect to N at fixed V and T if you have a one-component system, but if one component is disappearing, another must be appearing. So the minimum you can have is a binary system where A is becoming B and B is becoming A. So the composition of dN1 is actually equal to minus change dN2 when you're doing things like that, as we will see later. But for a multiple component change, I just introduce a chemical potential term for change in each of these components, and then the individual chemical potentials can be identified for change in composition of each individual type, where the other ones are being held fixed while one is varying. Finally, and turns out to be most importantly, let's play the same game on the Gibbs function. And hopefully we'll see at the end why this is the most important representation of the chemical potential. I begin with the fundamental equation for the increment of change of the Gibbs function, VdP minus SdT. This is the expression as it is written for physical change. I'm squeezing on the material and I'm heating the material, but I am not allowing the material to change composition under this representation of its increment of change. Then, since it's an exact differential, of course, I can write it in the form of a two-function dependent variable change, as we've done many times over now. So now, on the third line, I'm going to introduce change in composition by putting a fudge factor, again named mu, times the change in composition that the material undergoes. So I just modify the fundamental equation to include change in the composition of the material that I'm using. I'm now doing the fundamental equation for chemical change. Now, since again it's an exact differential, I can express mu in terms of other variables by comparing to the exact differential equation to find that the chemical potential can also be expressed as how the free energy varies with composition, but now under the auspices that the pressure and temperature are held fixed. Now, why this is our favorite form of the chemical potential is because when I'm working on a laboratory bench, I'm working in a laboratory that is at a fixed pressure and is at a fixed temperature. So this form of my chemical potential is far and away the most utile form of the chemical potential, and it's the form of the chemical potential that we will almost invariably invoke when we're going to use this quantity because of its connection to typical laboratory conditions. Now, that is not to say that this value is not the same value that you can obtain from the enthalpy free energy or Helmholtz energy or internal energy. It's just that when you obtain it from those thermodynamic quantities, you're doing it under different conditions than you are in this more utile form. Okay, now then finally, if I have multiple components undergoing change, I just introduce a fudge factor term for each of those components, and then from comparison with the exact differential equation, I can identify each of those individual chemical potentials from the expression. Where can we get numeric values for these chemical potentials? Well, let's start with the chemical potential of a pure substance. And we will represent this chemical potential from the most utile form of it, since the conditions are most commonly the setup that we use in laboratory of constant pressure and temperature. We will look at the chemical potential as expressed as from the Gibbs function. It's dG/dN at fixed P and T. Then we note that if a substance is pure, then the Gibbs energy of that pure substance can be expressed as N times the molar Gibbs function for that substance. So the extensive value G is the intensive Gm or molar Gibbs function times N. So mu is equal to the partial of N times Gm dN. And when I then look at that more closely, I get N, using the product rule, N times the partial of Gm with respect to N, plus Gm times the partial of N with respect to N. And I find that mu equals Gm. Now, the intensive form of the Gibbs energy of a pure substance happens to be equal to its delta G of formation. So the chemical potential of a pure substance is assigned from its free energy of formation. Now, what this is stating then is that the chemical potential of elements in their standard state is 0. That's okay again, because remember, if I'm going to do any other reaction, I'm going to maintain, according to Dalton, the fact that the composition of the reaction is that no atoms are lost or thrown into the pot, they're just rearranged. So there's going to be G values on the right side of the equation due to the atoms, and the same number of G values on the left side of the equation due to the presence of the same number of atoms. So if I subtract them to get delta G, and I've told you many times over, the relative values are more important than the absolute, so delta G is much more important than G itself. And so these values are going to subtract out anyways when I'm going to determine them. And I really only need to know the formation value of anything other than the elements, the actual materials that are undergoing the chemical change, because the number of atoms on both sides is always conserved. Okay, so the take home is that the chemical potential of any material is found simply from its delta G of formation. And so this is good for 298K and 1 bar. I know the chemical potential of pretty much anything I want. Now then I can put those things in combination and get the chemical potential of some overall reaction, as we will see. Now also then to note, the chemical potential of elements in their standard states is therefore 0, which doesn't bother me so much. We just assigned them to be 0 because in a chemical reaction they would have subtracted out on the product and reactant sides anyways. So I don't really care what they were to begin with, because they would have been gone in a typical chemical process where atoms are conserved. Gibbs himself did a lot of pontificating on the chemical potential, particularly the chemical potential derived from his thermodynamic function. And one of the things that Gibbs expressed was that the chemical potential is the same throughout a sample of a substance, and in particular of a particular utility when two or more phases are present in equilibrium, like a liquid with its vapor above it, then the chemical potential is the same throughout all phases in equilibrium simultaneously. So if we were to look at plots of the Gibbs function with temperature, remember that what we saw a little while back was that dg dt at fixed p is equal to minus s. So since we can relate, if this is a pure substance now, G being equal to N times GM, I will get that I can figure out that the change in chemical potential with respect to temperature at fixed pressure must be equal to the molar entropy. That's the only difference between looking at dg dt fixed p and d mu dt, or the change in chemical potential with temperature at fixed p. I will just change the entropy to the molar entropy. So, of course, then, what I would note that if I plot mu versus t, that the slope of the plot would be negative. Why? Because the molar entropies are positive, but with a negative sign in front. And I would note that the slope of the solid line is the least dramatic, liquid more dramatic, volume or gas even more dramatic. Then I note from those plots that there are really points where all phases are in have the ability to exist at the same time, but I note that in each regime, one phase has a lower chemical potential value than all other phases. I also note that there are crossing points where the chemical potential of materials are exactly the same. There's a liquid vapor crossing point, there's a solid liquid crossing point, and I'm seeing here a liquid solid crossing point. Now actually, if I extrapolate them back far enough, I can find, if I would like, I actually do see, sorry, the solid gas crossing point. Now, what I would learn is that those points where they cross means that those phases are in equilibrium at that point. So the temperatures which correspond to those points must be the points at which this material will freeze, the points at which this material will boil, and the point at which these materials would sublime. So these equilibrium temperatures have to correspond to those conditions. Now, remember, materials might not sublime unless the temperature conditions are correct to allow them to sublime. So there might be some weirdness as to how these are ordered, but there's going to be some temperature. You'll notice there's some pressure conditions under which these curves would be crossing. Let's use the chemical potential to describe one of the most interesting phenomena of nature, and that is the interesting behavior of the variation of the freezing point of water as you apply pressure to water. Okay, so these graphs might be a little bit hard to interpret, so let's look at what I'm plotting on both of them. I'm plotting mu versus T, chemical potential versus temperature, on the left and right for two different types of substances. Now, first of all, remember that dg dp at fixed T will be equal to the volume of the situation, and then what I can note that is if I just take that to a situation where I'm looking at the chemical potential instead of the Gibbs function, I will say that d mu dp at Vix T is equal to the molar volume instead of being expressed in terms of the Gibbs function. Okay, so then I have lines representing how the chemical potential of these materials varies with temperature. Now, these have negative slopes because in actuality, dg, or if you like, d mu dt is equal to minus s. So the reason, first of all, that these have negative slope is that d mu dt is minus s. And you'll notice that the slope of the liquid curves is more dramatic than the slope of the solid curves in both the left plot and the right plot. Then I'm going to look at how these chemical potential versus temperature plots vary when I change the pressure. Then it is a function of the volume. So when I squeeze on a material who will have an increase in volume in the liquid phase compared to a solid phase. Okay, so let's say that like most materials experience, they occupy bigger volumes when they're liquids than they occupy when they're solids. Typically something will, when it solidifies, let's say I have molten iron. When molten iron solidifies, the solid iron falls to the bottom. Why? Because the density of solid iron is greater than the density of liquid iron, and gravity has a greater force of attraction to it, pulling it to the bottom. This is true for gold, true for silver. Liquid silver is less dense than solid silver, so when you solidify solid silver out, it collects on the bottom. So since the density of solid silver is less than the density of liquid silver, the density of solid silver or iron is greater than the density of liquid silver or iron, that's because the volume of liquid silver or iron is greater than the volume of liquid silver or iron. The density is less for the liquid because the volume is greater for the liquid. So then if I look at how dg, dp would vary, and since it varies with volume, that means the variation of the liquid sample will be more dramatic. Notice the blue arrows on the left of the expression. There's a bigger blue arrow for the variation of chemical potential with pressure for the liquid than the size of the blue arrow for the variation of chemical potential for the solid. I have a mu at P2 and a mu at P1, and you note for the solid that's a little change compared to the mu at P1 to the mu at P2 for the liquid. Now, then what I need to do is note the point of intersection at P1 and P2. Those will be the melting points of typical materials at pressure 1 and pressure 2. I see that the melting point at pressure 1 is lower than the melting point at pressure 2 for generally all substances. This kind of makes sense. If I put more pressure on top of them, I'm going to have to put a higher temperature into them to begin to get them to change phase from solid to liquid. Now let's go to the right side curve. The right side curve represents the behavior for water. Water is a material where the volume of the solid is greater than the volume of the liquid. Now that might seem weird, but just think about ice. Ice floats. That's because ice solid is less dense than water liquid. So it rides on top of the liquid water. This again is because the volume of the solid is greater than the volume of the liquid, so the density of the solid is less than the density of the liquid. So now I have curves representing the chemical potential with temperature. They are negative slopes because the mu dt is equal to minus s. The curves are more dramatic for the for the liquid than they are for the solid, because the entropy of the liquid is greater than the solid. So the curves are more dramatic for the liquids than they are for the solids. But now when I change pressure, the blue arrows are indicating how the chemical potential of the liquid and solid will vary when when pressure is changed. The mu dp is a function of V, and it's a positive function of V. So when I increase the pressure from P1 to P2, there's an increase of the chemical potential. But notice now the increase of the chemical potential is greater for the solid than it is for the liquid. So now I look for the intersection points of the mu curves at P1 and the intersection points of the mu curves at P2. Now what I see is that the freezing point, or the point of melting of the material at the lower pressure, is greater than the melting point of the material at the higher pressure. That's very interesting and very unique to water. I know of no other material that exhibits this kind of behavior. Now what this means is that if you're rolling across ice on, say, some skate blades, which has dramatic pressure increase under the surface of that blade onto the surface of the ice, what you will do is, due to this dramatic increase in pressure for that, you will lower the freezing point of the water so dramatically that very quickly a layer of liquid water forms and the ice skate slides very easily on that liquid layer that you've generated between the blade and the ice. So this again is a unique phenomenon, very clear, or only occurring pretty much with water, and pretty much only occurring because the volume of solid water is greater than the volume of liquid water, and it can be explained based on these behaviors with the chemical potential. Let's look at how the chemical potential can be expressed as a function of pressure change. So I begin with the fact that since dg dp is equal to, at fixed t, is equal to V, and then I can express this in terms of the chemical potential from the molar volume. D mu dp at fixed t is equal to Vm. Well, then I can just state by multiplying both sides by dp that at constant temperature, d mu is Vm dp. Then I can use the ideal gas formula for Vm for the vapor that I have present, and Vm is RT over P, so d mu of the gas is RT over P times dP. Now I'm going to assume that the gas and liquid phases are in equilibrium. If they are in equilibrium, the chemical potential of the gas phase is the same as the chemical potential of the liquid phase. This will allow me to model the chemical potential of the liquid from what I know about the chemical potential of the vapor. This is a very powerful trick. Liquids in general are very hard to model. However, gases, as we know, we have several models for gases. So this enables us, as long as we have liquid and vapor in equilibrium, we know that the chemical potential in those phases are the same. So we can use our simple gas phase models to get information about what's going on in the liquid. Now what I'm going to do is I'm going to divide, I'm going to move things around a little bit and write it in the form RT dP over P is equal to Vm of the liquid dp. And since again these are state functions, I will just go from pi to pf on both sides. Now I'm writing it some weird way, p1 plus delta p for p2 on the right, but that doesn't even matter. I could just wrote p2 to p1 on the right for the change in pressures placed on the liquid to give the change for the change in pressure that this will experience when I'm done. So I get when I'm done there, by integrating both sides of this equation, that RT ln PF over PI, because the integral of the left is an ln expression, where the integral of the right is just PF minus PI, or delta P plus PI minus PI, if you like. So I get RT ln PF over PI equals Vm of the liquid delta P, and I can rearrange this by taking the inverse ln of both sides, or the exponential of both sides, and I get PF equals PI exponential Vm of the liquid times delta P divided by RT. A little exercise where we examine this. I have a 298K. I have pure water that has a vapor pressure 23.8 millimeters of mercury. What will the vapor pressure above the liquid become if the liquid phase is subjected to an additional 100 atmospheres of pressure above the normal 1 atmosphere of pressure? So what do I get for Vm of the liquid? It's the molar volume of the liquid. Now, where did I come up with this number? Well, remember that the 1 mole of water occupies 18 milliliters. How do I know that? Because the density of pure water is 1 gram per milliliter. So 1 mole of water is 18 grams of water. 18 grams of water is 18 milliliters of water. And then to put it into SI units, that is 0.0180 liters per mole. And that will be sufficient to use in the ideal gas representation of this formula. So Vm of the liquid times delta P will be 1.8 liter atmosphere per mole, 1.8 liter atmosphere per mole, because remember, my delta P is 101 minus 100, or 100 atmosphere change in pressure I'm applying to this surface. So I have 182 joule per mole for my Vm delta P term. After I convert that into from liter atmospheres per mole to joule per mole, how do I do that? I multiply by 101.3 joules per liter atmospheres, and my 1.8 liter atmosphere per mole becomes 182 joule per mole. Now I just stick that into my formula, where my PI is the initial vapor pressure, 28.3 millimeters of mercury, times this exponential term, and I will note that that dramatic increase in the pressure on the surface of the liquid water will increase the vapor pressure to 30.5 millimeters of mercury. Let's examine the consequence of a vapor and liquid phase in equilibrium, which means that the increment of change in the chemical potential of the liquid and vapor phase is the same. And since we can write the chemical potential as a function of the molar Gibbs function, as we have described on the previous several pages for a pure substance, then since G is equal to VdP minus S dt, mu is equal to Vm dP minus Sm dt, where the subscript m means the intensive molar quantities representing those those thermodynamic quantities. So we will set Vm dP minus Sm dt equal for the liquid and vapor phases. Then we will gather the terms in dP and dt onto each side of the equation. Then we will divide both sides by dt and divide both sides by the change in volume. And we arrive at what is known as the Clapeyron equation, which holds for any boundary, which is an exact equation. No approximations to this point have been made. So this holds not only for the liquid vapor phase boundary that I talked about here, but it holds between the solid vapor boundary as well for materials that might be subliming. And it actually holds for the liquid gas the solid liquid, boundary as well. And that is the fact that the differential of pressure with respect to temperature must equal the change in entropy divided by the change in volume. Now again, if I go to different phase boundaries, I would change this to dP dt is delta S of sublimation divided by delta V of sublimation, or I could have dP dt equals delta S of melting divided by delta V of melting if I wanted to go to different phase equilibrium. So just repeating from the last slide, I have my dP dt is delta S over delta V, and again, really technically, this can be concluded for any equilibrium between two phases, whatever phases you choose to make. So now what I'm going to do is recognize that the entropy of vaporization is equal to the enthalpy of vaporization over T at that phase boundary transition. So that'll be the boiling point temperature if I'm looking in particular here at the liquid vapor phase boundary, but I could have put delta H of fusion divided by T of melting, and I can have the same equation valid for going between a liquid and a solid. And I could also put delta H of sublimation over T of sublimation and have an equation valid from going directly from a solid to a gas if I wanted to. Okay, so far the top line is truly completely general. No approximations have been introduced into the Clapeyron equation at all. But now Clausius said we can do the following things to Clapeyron's equation, and what we can do is we can recognize, at least for this phase boundary in particular, this would also work for sublimation, but for this phase boundary, delta V vaporization is equal to Vm gas minus Vm liquid, and of course that's got to be true, and since the gas occupies so much more space than the liquid, I can approximate that as Vm of the gas. And if the gas is ideal, Vm is RT over P. So dP dt will be P times delta H over RT squared when I substitute in for V molar of the vapor. Okay, so the approximation so far has been ignore the liquid phase volume compared to the gas, which again, remember I argued a few slides back that water in the liquid phase occupies 18 milliliters. Water at STP in the vapor phase occupies 22.4 liters. That is 1,000 times more volume. So that is a valid assumption to say the molar volume of the liquid is way greater than the molar volume of the gas is way greater than the molar volume of the liquid. And now using the ideal gas formula, I get dP dt equals P delta H vape over RT squared, which when I rearrange and separate variables, remember this is our big trick, I'm going to put the differential with respect to P on one side, the differential with respect to T on the other side, and then I can integrate both sides. And the integral of 1 over P is ln P, or when I'm rearranging that, I can do the change of variable. the dln p dp is 1 over p. And so if I take that and put the pieces together, dp over p, just rearranging, is dln p. And also I can make a change of variable using d1 over t dt as being minus 1 over t squared. Solving that, I get dt equals minus t squared, d1 over t. So for dp, I'm going to make dp over p, I'm going to make the substitution dln p. And for dt, I'm going to make the substitution that is equal to minus t squared d1 over t. So the equation can now be written dln p d1 over t equals delta H of vaporization over R, or minus delta H of vaporization over R, excuse me. On the previous slide, we found that approximating the phase boundary between the liquid and the vapor, we come to the conclusion that dln p over d1 over t is equal to delta H vape over R. And of course, the left-hand side of the equation looks like a slope. So if I plot that logarithm of the vapor pressure of a liquid on the ordinate axis and the 1 over the Kelvin temperature, that is, on the abscissa or x-axis, it should be linear, negative, because of delta H and R. Delta H of vaporization is a positive quantity, R is a positive quantity. So the plot of ln p versus 1 over t should be negative slope, it should be linear, and the slope should have a value of minus delta H of vaporization over R. Now we can see that by literally integrating both sides of this equation, and that's what I do underneath the graph. And what I find is that the ln of pf over pi, when I integrate from the limits of pi to pf, I will get that that is equal to the change in temperature delta t, or delta 1 over t, when I do that integration. Remember, the integral of dt over t squared, t here is n is equal to negative 2. The integral of x to the n is x to the n plus 1 divided by n plus 1. So the integral of 1 over t squared is negative 1 over t, evaluated at the limits. So I end up getting the expression that you see at the bottom. ln of pf minus over pi is delta H over R times the difference in the temperatures.